I'm Mridu, and I'm a sophomore in computer science.
And today we will talk to you about ARTEMIS, AI-driven robotic triage labeling and emergency information system. This is a project we worked on this semester and submitted to a conference at IEEE-IROS 2024. In 2023, the United States saw 9 mass casualty incidents, and this resulted in over 100 deaths. And first responders are tasked with the challenge to increase their efficiency of attending to victims and in a time-constrained manner. To help them do this, there's triage classification. This is the process by which we assign priority to attending to victims in a disaster or mass incident. This is an example of a triage label, and triage is usually in a number scale. So here we have an ESI 5-level triage, which has a 5-level priority system. That's what we'll be using. And in the past decade or two, we've seen robot capabilities improving immensely. Here we have parkour being performed by robots, and robots are able to traverse complicated, unknown, rugged terrain really well. So how can we leverage robotics and AI to assist first responders in a mass casualty incident to improve their efficiency of triage?
There has been work done in the past to improve the process of triage classification. As we see from work in the past, machine learning models like the one proposed by Revanth et al. Has achieved an accuracy of 66% in classifying the acuity or the severity level of a patient's condition given their medical data.
And as I mentioned before, robot capabilities have improved immensely. So there's been recent cases where people have used robots in like hazardous leakage environments or firefighting, for example, to improve the efficiency of attending to victims. But ARTEMIS, what do we contribute, right? We have 4 key contributions. Number 1, robot-driven victim identification.
And number 2, an AI-based triage classification system that's rapid.
And number 3, a graphical front-end that's visual for first responders to see victim information.
And last but not the least, a synthetically augmented data set that we prepare from the YMED.
Let's step into the methodology. So this is the full pipeline of ARTEMIS, and it has 3 major components. Number 1 is a human detection, number 2 is triage, classification, and number 3 is data display. So we're going to step into these 3 specific methods, stages in detail. First off, human detection. This is done with the help of a media pipe blaze pose detection algorithm. So what this does is it detects pose markers with an RGB camera used in the environment, and it finds human pose markers and marks them. And we use those on the trajectory controller for the robot. So with that in mind, let's set up the robot, right? We have ultrasonic sensors the robot already has on board. The robot also has an IMU, or an inertial measurement unit, to keep track of its location and trajectory. We also use an external camera to put the pose trajectory algorithm, and it comes with a microphone as well, so we can use speech input from the human. So let's write the algorithm now, since we have the robot set up. All this algorithm does is it searches for humans in the environment, and then it approaches them. And this is done in an efficient way, as to not visit like previously visited victims as well. One thing to note is that collecting vitals from humans is a part of this structure, and this has been proven in the past with existing methodology and hardware. ARTEMIS does not include this, but this can just be plug and play. It can literally be implemented on top of the robot, and this can be this.
Then we move on to stage 2, which is the acuity labeling of patients given their medical data. So the quadruped has been leveraged so far to go out into the field and capture data from patients in the MCI setting. Now we want to use that to train machine learning models that will then predict the acuity or the severity of the patient's condition in order to allocate resources to them. And in order to do so, we performed experiments on the YMED dataset. Now the YMED dataset is a publicly available dataset collected by Yale New Haven from their emergency department. And however, there are some challenges associated with the YMED dataset. It has significant class imbalance. So the class will be defined as the acuity level, and so there's 5 classes. So each of these classes has a varying amount of data associated with it. For example, from this pie chart, you can see that there's up to 44% of the data set is comprised of data points from acuity level 3, which is way more significant than acuity level 1, which comprises only 0.1% of the data set. In order to combat this disparity, we had to perform synthetic data augmentation to even out the differences and make sure that the machine learning model doesn't learn from the skew of the data set. So we performed SMOTE, which is a synthetic minority oversampling technique, which was developed by Chawla et al. That basically randomly and intelligently generates points between pre-existing data points in the data set. So class purple, which is acuity level 1, is the minority as we established previously. You can see that it's heavily been upsampled and in a manner that preserves the relative ordering of the original points.
And the final stage is displaying results. In this case, we have a graphical user interface that shows all the victim information necessary for first responders. So it contains victim location, trajectory, along with some images of the victim and some speech input that has been detected by the speech detection. But the most important is the acuity label. That's the final column order that shows what the first responders need to give the priority for each victim. So let's step into the human detection experiments and results. I'll show you a video now that demonstrates the ARTEMIS deployed in a real experiment. Hopefully the audio works.
Please state your symptoms.
Knee injury, hip injury, leg pain.
Thank you for your input. Help is on the way.
So the robot gets the input, finds the next victim, approaches them.
Please state your symptoms. Help is on the way.
So yes, the last person was unresponsive. So we also show ARTEMIS deployed on a gazebo ROS simulated environment. We have an MCI setup, and the robot approaches humans and is able to, walk towards them, and walk towards the next victim, and so on.
Then we move on to the experiments and the results that we performed in stage 2 of our pipeline, which is the acuity labeling section. We had to build machine learning models, try and test them out, see which one works best in order to deploy in ARTEMIS. And in order to do so, we worked on the YMED SYN Plus dataset, which is the one that we synthetically augmented from the original YMED. And this contained medical data for patient information like heart rate, respiration rate, oxygen, O2 sats or oxygen saturation, blood pressure, and it also contained acuity labels for every single data point. So we had a ground truth that we were working with. And we essentially created and trained 4 machine learning models. The first one was a support vector machine, and then we trained a Gaussian naive Bayes, we trained a random forest, and finally we also trained a multi-layer perceptron or your regular neural network. The main thing to note about these graphs is that the prominence of the diagonal of each one of these plots indicates how accurate a certain model was. So you can see that the support vector machine and the Gaussian naive Bayes were not that accurate in predicting the actual acuity level of a patient in an MCI setting because they have very weak or sometimes non-existent diagonals. However, the random forest and the MLP, they have a pronounced diagonal. The MLP performs better than the random forest, as you can see. And indeed, it does have an accuracy of 74%. However, accuracy is not the only measure we're interested in while determining whether a machine learning model is efficient. We're also concerned with the precision of a model. For instance, as you can see from the graph of the MLP, among the points that were misclassified by the MLP, about 84% of them were either one acuity level above or one below the true label that it was supposed to predict. So this is pretty accurate, and this is a error of margin that's small enough that it doesn't significantly redirect the resources away from a particular patient or towards a different patient. And finally, we can also compare ARTEMIS with state-of-the-art models, and we in fact outperform other models like the KTAS, which was a model developed by Choi et al.
Finally, to conclude, I'd like to restate our identification algorithm, an AI-based triage mechanism, a graphical front end with victim information, and a novel synthetic triage dataset that people can use. For the future, we'd like to improve on ARTEMIS and make it better. So one thing I mentioned before was the existence of hardware to collect vitals from humans. We'd like to actually put that on the robot and test it to create a full system. Number two, we can use a better data set that's more tailored towards an MCI-based triage environment rather than emergency department, which is what we have our current data set in the system, to make it more applicable again. And finally, the integration of this robot system with other robots in an MCI, so such as drones or other teleoperated robots that other people are using as well to navigate in an MCI. So robotics can assist first responders in MCIs for triage classification to improve the efficiency of attending to victims. And this is the conclusion of our